This video explains how to determine whether a chemical reaction is spontaneous or not using the second law of thermodynamics. Alright, in previous videos we have seen how to calculate the change in entropy for a chemical reaction. But that calculation referred to only the system. If you want to determine spontaneity, then you actually need to calculate the change in entropy in the entire universe as the second law states. Right, so remember the universe is divided in a thermodynamic sense in two parts, the system and the surroundings. So we know how to calculate the change in entropy for the system in a chemical reaction. That's just the change in entropy as you go from reagents to products. Okay, so the other piece that is missing is just how to calculate the change in entropy in the surroundings. So this video is going to illustrate how to do that for the case of the combustion of sucrose. Alright, so again, for the system, we already know how to proceed. This is simply going to be the sum of the molar entropies of products multiplied by their stoichiometric coefficients minus the sum of the absolute molar entropies of reagents multiplied by the stoichiometric coefficients. Okay, what about the surroundings? Well, for the surroundings, we're going to use the usual definition of change in entropy. So change in entropy for the surroundings, I'm not going to write any subscripts here as molar or reaction. We'll do that later. This is a general definition though, and this is just heat in the surroundings over the temperature, which for this case is going to be 298 Kelvin for that particular reaction. Okay, so we move forward. Then the heat in the surroundings is equal to the minus heat of the system. They're in thermal equilibrium, and every joule exchange or given off by the system will end up in the surrounding. Every joule absorbed by the system comes from the surroundings, so that equality is correct. And then for the next step, we just have to remember here that we're working our chemical reactions generally under isobaric conditions. That means constant pressure, and we know that heat at constant pressure is simply the change in enthalpy. Okay, over to you. Okay, so now is when we're going to start to write subscripts and so forth, right? So notice that we're going to be interested in a reaction. This is going to be a molar quantity, and generally we're going to be working under standard conditions. So what that means is that our change in enthalpy will be the molar change in enthalpy for the reaction under standard conditions. And this is something that we have learned to calculate using arguments of the first law. I'm just going to repeat here, right? So remember that the change in enthalpy for a chemical reaction, molar standard, is simply the sum of the enthalpies of formation of products minus the sum of the enthalpies of formation of reagents multiplied by their stoichiometric coefficients. Okay? So here you have a table with the enthalpies of formation, standard state, for all of the species involved in the combustion of sucrose that we have right there. And when you actually do that calculation, this number turns out to be exothermic, so that means this has a negative sign right there. So there's going to be 5644 kJ per mole. Now this is simply the enthalpy of the reaction, but it's something that you need in order to calculate what the change in entropy in the surroundings would be for this particular reaction. Okay, so taking that expression forward, we're going to find here that this delta S, the surroundings, which is a molar quantity, and we're doing the standard conditions, is going to be equal to this minus 5644 kilojoules per mole divided over the temperature, which is 298 Kelvin. So you get to a positive value of the change in entropy in the surroundings, plus 18.9 kilojoules per mole Kelvin. Okay, so let's then see what this sign really means here. Okay, so what that sign means is that somehow the surroundings are gaining entropy from the reaction. And you can easily understand that when you consider that the reaction is heavily exothermic, right? So on a per mole basis, there's a lot of energy that is being dumped into the surroundings. And what that means is that that increases the entropy of the surroundings, right? Those surroundings, there has to be an energy dispersal in those surroundings from that energy that is being dumped into them, right? So that just justifies this positive sign right here. Okay, so the only then remaining piece to determine the spontaneity of a reaction is simply to put together the change in entropy in the system, the change in entropy in the surroundings, to figure out what the change in entropy in the universe is. If that change in entropy in the universe is positive, then the reaction will be spontaneous as written. If it's negative, then it won't be. And then if it's zero, that will be a reaction at equilibrium. Okay, so let's carry out that final calculation so that we can determine exactly how that works for this particular reaction. Okay, so we have here the two pieces, the system and the surroundings. So I'm going to just write here delta S of the universe is going to be equal to delta S of the system plus delta S of the surroundings. And again, we just put them together. Now notice that there's a difference in the units that we're using for these two quantities. Notice that for the change in entropy in the system, we actually, the number that we were getting was joules per mole Kelvin, but the change in entropy in the surroundings we just calculated is kilojoules per mole Kelvin. So make sure that you have that those units be equal. All right, so I'm going to change that to kilojoules per mole Kelvin, so that will be 0.5119 kilojoules per mole Kelvin. And then change in entropy in the surroundings, so plus 18.9 kilojoules per mole Kelvin. What I find here is a result of plus 19.4 kilojoules per mole Kelvin. So the conclusion is that the combustion of sucrose at 298 Kelvin and 1 bar of pressure is spontaneous. Okay, so that's what we can conclude from here. Now notice that thermodynamics does not tell you whether a reaction happens fast or slow. That's the body of kinetics. Thermodynamics only tells you that the reaction should be spontaneous. Okay. One very important thing that the thermodynamics is also telling you is that the reverse reaction, as written, will not be spontaneous, right? If you set up this reaction as these being the reagents and that the products, then the change in entropy of the universe will be exactly this number, but with negative sign. And what that means is that generating sucrose from CO2 and water will not be spontaneous at 298 Kelvin and 1 bar of pressure. Okay, so that's the conclusion as well. All right, so let me wrap up. In this video, we have seen how to determine the spontaneity of a chemical reaction. You need to apply the second law, and that involves the calculation of the change in entropy in the system, the chemical reaction, and the change in entropy in the surroundings, as we have explained in this video.